So this topic actually covers two things kind of at the same time, but I think they go together kind of naturally. So I put them in the same lecture, and you'll tell me if you think it's a good fit or not. So we're going to cover two things. We're going to cover nonlinear modeling, which means going from just lines fitting our data to now things beyond lines, curves and all sorts of shapes. Because the reality is a lot of data does not really classified or fit just straight lines that well. And this is going to bring us to the notion of a little bit more formal notions of overfitting. And so when a classifier overfits and when you sort of overfit a training set versus a validation set. So we'll talk about cross-validation and how you kind of monitor overfitting and how you know if you're overfitting or not. And then we'll talk about regularization, which is another way to avoid overfitting and another sort of method of avoiding complexity of classifiers. So before I start, so we're going to first cover an example of peak power prediction, again, peak demand prediction, then cover overfitting, generalization, cross-validation, and then cover regularization, as well as general nonlinear features and nonlinear classification. These two will probably be a little bit next time. Before I start, though, a few quick announcements. The tutorial proposal is due tonight. So remember, this is a one-sentence summary of what you're going to want to work on in the tutorial. We will give feedback on that. So by next week, I'll send feedback on all the topics you propose, including if you're worried about your topic, and you want to do it, but you're not quite sure if it fits, you can go ahead and propose it. And I'll sort of say, yeah, that's not really appropriate for data science, or I'll say probably it's fine and try to give you some suggestions. I'll also be brief in my responses back to you because I have to cover everyone's in the span of a week or so. But I'll try to have that by next week. You can change topics after that, especially if I sort of say, this probably is not the best topic for this course. Maybe you want to consider something else. But don't submit with the intention of doing that. We have that list that I mentioned last time of tutorial topics that you can check out. Not the actual notebooks. That was intentional not to have those. Maybe when this is all over, I can put them back up. But for now, I didn't want people to sort of look too much at what wasn't done before. And then you can change, but don't submit with the intention of changing. Use the opportunity to get some feedback, and hopefully you have the right one. Okay, note number 3. There was I think a sort of poorly and no real reason to write it this way, confusing point on homework, on linear regression homework, in particular point 3 about the Cholesky decomposition. It just dealt with something I didn't really want to deal with at all, so I posted a clarification note on Piazza. It's pinned on Piazza. The point is you can just use np.linealis.solve to solve the least squares problem. You do not need to use Cholesky decomposition. You can if you want to, but you don't need to. And if you're going to, by the way, I referenced some other functions you should check out, not the ones that's in NumPy, because there's just problems with that. So that was sort of that was much too confusing, and sort of nothing actually changed in the back end. Just you could always pass with np.linealis.solve, but just know that you can do that. And then finally, there's been some confusion about TA office hours. They've been posted on Piazza, but they do change them sometimes, and there wasn't really an easy way to check when all of them were. So now on the web page under instructors, we have a Google Calendar of all the TA office hours for every week. And if they haven't changed it, they will change it on there. So they will, for that week, drag to a different time, and so it's been changed. That should always happen 24 hours before, but there are some emergencies sometimes. So check it before you go to office hours, just to make sure that they are in fact there. But they have both the times and the locations and all the TAs that are giving them. I actually have not. I will put my office hours when I know when they are. They're still variable times. I have to find the room every week, and kind of depends on the other meetings I have on Fridays, so they will change. I try to post those always on the Thursday, sometimes the Thursday before that Friday. I'll send out another reminder this week. I had them last week, and both the homework was just out, so maybe people didn't really want to come, but also I didn't actually post or notify everyone about them, so people might just not have realized I was holding them again. But I'll have them again this week, and you can come to those, especially now that the homework's due on Wednesday. You can come to them and use them as a resource for this upcoming homework. Okay, any questions about logistics stuff? All right, so let's just jump right in to nonlinear modeling. All right, so the way I want to motivate this is that when I first kind of described linear regression, I motivated it with this application of predicting the peak demand. This is the actual peak demand from Pittsburgh with the temperature in Pittsburgh. And one thing I sort of said, but maybe didn't quantify too, or didn't highlight too much, was that this is only for the months of June through August, right? And in June through August, the power in Pittsburgh is largely driven by air conditioning. And so you kind of expect that with a higher temperature, things would keep going up. And we kind of fit a line. It looked kind of like this. I don't think I have a slide with it on this one, but the line kind of went through this data as you would expect it to. But obviously there's something kind of wrong about this, right? And that if we try to apply it to the current time, I guess modulo the fact that we actually are in pretty high temperatures these days. But if a normal day in the middle of February, if you try to apply it to, it's not going to be very accurate, because at the high temperatures, of course, 40 degrees, that would say the power just keeps going down and down while you have lower and lower temperatures. Eventually, I guess, with low enough, it'll start generating power. You'll start actually consuming negative power because this is what the model predicts, because obviously it doesn't know anything about the winters. So let's go ahead and add now the actual winter months and see what these look like, not just for the summer, but for all months. So here's actually the data for all months. And this is, again, this exact data is actually in the notes. So it's like the actual data, raw data itself that I just downloaded from both the weather site and the system, the system operator that runs Pittsburgh's utility. So you sort of see the raw data. And this is just the raw data for the past 5 years of power consumption versus high temperature. So this is kind of what you expect, right? So after, I was showing kind of this part before. But after a certain point, power does not keep going down forever. It kind of levels out once you reach the point where you don't run air conditioning anymore. And then it kind of creeps back up. Some people have electric heat. It's not very common here because it's very expensive. But, also in the winter, we turn on lights more because it's darker. And so there's all sorts of interesting correlations here. So the power actually starts going up a little bit now as it gets colder and colder. And now if we fit a linear model to this, or a pure linear model, it looks kind of disappointing, right? Because it does not capturing any of the actual structure in that data there. It is the best least squares fit for a line that we can come up with, but it doesn't actually capture any of the interesting features there. It just sort of says, it gradually increases, and that's of course not the actual pattern you see. And so what we're going to talk about today is ways to do nonlinear modeling of functions like this. And I'm actually going to put nonlinear in quotes here, because although these are, in some sense, nonlinear models, you think of them as kind of like nonlinear fits to your data, it's actually still all under the rubric of linear models as far as machine learning goes. And the trick that we're going to do here is that we're going to construct features, our inputs, that directly capture nonlinear functions of the underlying input. All right? And we'll actually define this a little bit more formally later when I call kind of the high temperature itself kind of the raw input, whereas this is sort of the features. But we won't worry about that for now. For now, we'll just kind of call them the same thing and just note that we are including nonlinear functions of the underlying data in with our features here. This is extremely common, and things like this are, of course, how you actually do a lot of machine learning problems in practice. So for this example, for instance, instead of just including the high temperature and I guess a constant term, we can include also a high temperature squared term. Okay, and if you have that term, so if I have high temperature squared, and I have my, let's see here, if I have my output, or my prediction really, is equal to theta 1 times high temperature squared plus theta 2 times high temperature plus theta 3 times 1, right? This is now actually, although this is still a linear model in that it's linear in the theta terms, right? Everything there is linear in the parameters. It's obviously nonlinear in the underlying data. We're actually fitting a quadratic function here to the underlying data. And this is actually going to be the trick about how you capture nonlinear effects with a lot of models. This is the trick about how you capture nonlinear effects while still having the benefits of linear models. So things like exact solutions, all these nice features about linear models, they still are maintained, despite the fact that we have nonlinear functions. For example, things like kernel methods, which I actually don't have anything in the slides, but I might try to add something for next time briefly. This is how these things all work. They actually use techniques from linear models still, but they basically are creating nonlinear functions of the input data. So with the same hypothesis class as before, so actually everything we did before is still going to apply here. So our hypothesis class is still the inner product of our parameters and our features. It's just that now this linear looking thing actually implies a nonlinear function of the underlying data. And that's how you capture, in the simplest way, nonlinear models on your underlying data. But of course, since the actual, from a standpoint of the parameters, since the model looks exactly the same, everything works out the same as it did before. You still have the least squares solution, for example, given by the normal equations, and things kind of work out okay. So here is a degree 2 polynomial fit now to our demand data. So it looks quite a bit better, right? Still not perfect. It's still sort of by necessity, quadratic functions. They have a linear term, but they're also sort of symmetric, right? They're symmetric around some point. And so this doesn't seem like a symmetric function. So we can, of course, just fix that by just going a little bit higher in polynomial degrees. So I'm going to show, so here's some code that does this. So actually, I haven't transitioned to this code yet, to the Python 3 notation yet. So I'm using dot there instead of the at symbol for it makes multiplication, but hopefully it's still understandable. Okay, so what I'm doing here is I'm actually doing a couple things. The first thing I'm doing is I'm just selecting the temperature as my kind of raw input x. And then in this case, I'm actually doing a little different normalization. I'm normalizing the features to be between -1 and 1. This is somewhat just arbitrary, and I know I've actually now used 3 different normalization schemes. One in class the first time, where I made the standard deviation one. One in the notes, where I make them between 0 and 1. And now I realize one again, where I have to make them between -1 and 1. The reason for this is that polynomials, in order to get sort of to see the nonlinear effects of them, you kind of want them to be in a range where they're not too big. If you start having like 10 to the, or x to the 50, if you ever get outside that 0, 1 range, they get really, really big. So it's better to always be within -1 and 1. That way they're all bounded in their ultimate value. But you also want to have a negative range there, because it also makes, the expressivity of polynomials comes a little bit from their ability to sort of have odd and even functions. Is what it really is. So mathematically, that actually is irrelevant. By the way, you could mathematically, you don't have to normalize at all. But in practice, just like with gradient descent, the numerics get, even with exact solutions, the numerics get very bad if you don't normalize like this. So you can try that if you want. In the notes, I'll actually show a little bit of what happens when you don't normalize. But basically, you start getting invalid solutions. You start having nans and stuff in your solutions, and no one likes that. So I'm normalizing again to make my raw, and x here is just my high temperatures. It's just a vector of all my high temperatures, but just that value. X here is just a scaled version of my high temperature scaled so the minimum value is -1 and the maximum value is +1. And then y here, I'm actually not going to normalize y. Y is just my daily load, my peak demand rather. Okay, so now I am going to create a feature vector of this sort of matrix x, where x is going to be a matrix that incorporates all my different degrees of my polynomial. So this is going to be, I'm using the v stack here, which means I'm just stacking one on top of the other, and then I'm going to transpose them. So it's really sort of stacking them vertically in some sense, or horizontally in some sense. But basically what I'm doing here is I am just creating a matrix of features such that the first column, I take my little vector, my vector x now, and I square that, or take it really to the power d for whatever degree it is. And that's that first column of this matrix. And my range here is from the polynomial degree I want down to 0, really, because it's one more than I want to do, and then it's going by -1. That's how I go from the degree d down to 0. So my next column is going to be x d minus 1, and all the way down to just having a column of x here, and then a column with 1 Of course, that's just, I get the 1 for free by just having my last polynomial degree being degree 0, always. Okay, and so importantly, I'm also normalizing before I apply the polynomial, not after. So the normalization happens before I apply this nonlinear function. And then I just form my least squares estimate. So solve x transpose times x transpose times y. My least squares solution, and that gives me my solution. Now, one other issue that comes up is you have to plot this function now. Before we could plot a line really easily, because if I had my data and I wanted to plot a line in matplotlib, I would just select 1 point down here and 1 point down there and draw a line between them, and it would draw it. Now, since I don't have a line anymore, I actually have to sort of select some sampling of points. So what I'm doing here is I'm actually selecting I'm creating an x sort of input space, which is a linear interpolation between the smallest x and the biggest x, also then normalized into the same range. So I'm applying the same normalization over that sort of range. And then I'm going to form the same kind of polynomial features on these raw sort of sequence of inputs that just span my entire range that I want to visualize. And I create my prediction here by multiplying that by theta. Any questions on that, on the sort of what was going on here? Okay, so I do this, and here's what I mean, and I got what I showed you last time for d equals 2. Here then is 3 equals 3, and again, all I'm changing, I'm running the exact same code here. All I'm changing is just this constant here, poly degree. So if I set that to be equal to 3, I get the next slide. If I just set it to the next one, I keep going. Okay, so this is polynomial degree 3. Looks good. It has a little weird thing down here. Though to be honest, the tails of this are always a little bit hard to get anyway by any model. So for the most part, this is starting to look pretty good, at least for the majority of data points. There's no real reason why you expect it to go down like that, but we can ignore that maybe. Here's 4. It's looking a little better. Here's 10. 10 now actually looks pretty good on the entire range of the data. It's still creeping up by this point. By here, it drops off. But again, you can't really, polynomials are really bad at extrapolating. So you don't want to worry too much about what's happening outside the bounds of your function. So this is all looking good. We're seeming to get if you sort of look at how this fit looks, it looks better and better until you get to this, which I accidentally skipped too fast. Until you get to this point here. So let's, we're doing well, right? We're doing pretty well here. This is degree 3, it looks good. 4 is a little better. 10's a little better, maybe even. So let's just keep going. And of course, something happens at some point when you hit polynomial degree 50, and it no longer looks so good. So now you have sort of some odd things here. You have some, lines here that are kind of going very squiggly here. You have this weird kind of oscillating pattern here, and it does all sorts of crazy things. So what's happening here? What's happening here is that this is actually a really good fit to the data as far as least squares is concerned. What you'll notice actually is that these points over here, which in some sense were kind of hard to get, but they're sort of spaced well apart, so there was some room to get them. We're actually doing really well over here. We're passing through these points exactly. I mean, I hit this one exactly, I hit that one exactly, I hit those two. Basically, I'm sort of passing exactly through those points. And so from a perspective of least squares error on this data set, I'm actually doing really, really well right now, right? So I'm doing sort of better and better the more I kind of improve, increase my degree upon polynomial. And in fact, what you can show is that if you have a set of m, we always have m data points, right? If your data points were all distinct, so they are all unique values, which is not the case here actually. Here, the weather is discretized to a certain number of temperatures. They have every possible temperature. There are actual bins, so you could never fit the data exactly in this case. But if you do have m points, which are all unique, then it's actually possible to fit your data exactly if you pick a degree polynomial of m. So if I pick polynomials up to degree m, in other words, m different features, I can always actually fit my data exactly. And the way to see this is just actually, I mean, you can see it for a number of reasons. But one way to see it is that if m equals n, then these matrices here are actually both square. So X transpose and X are both square matrices. We're assuming if the points are distinct and you use polynomials, then at least in mathematical terms, you can actually prove that those matrices are individually invertible themselves. We won't worry about that, but just trust me that they actually are. And so you can actually apply kind of the rules of inverses where you move this inverse into these two things. So I form, X inverse, X transpose inverse. I have to flip the order when I invert a product of matrices. Times X transpose times Y. These two things cancel out here, and you just have X inverse Y. And that means, by the way, that X times theta, which is my prediction, is always equal to Y. Okay, so I've basically found a solution that has 0 error. Keep going, but you, of course, won't get lower than that, right? And in fact, it's the case kind of trivially in some sense that in terms of minimizing error, remember, my goal here of a machine learning problem is to minimize my error, right? So I'm minimizing over my parameters the sum from I equals 1 to m of my losses. Right? So this is the problem I'm solving here. And oops, move it down a little bit. And of course, if I add another degree polynomial, I can only decrease my loss, right? Because I've added, I could always have the exact same functions before by just setting that coefficient to be 0. So I have a strictly greater representational power than I had before. And I'm always going to kind of decrease my loss on the data that I'm actually trying to fit here. So that seems somehow wrong, right? It doesn't seem like we really want a line that passes through this, because there's some notion under which, even though it's good on these data points, we sort of think of there being kind of a continuum of actual underlying data points here. And on this point, it's actually quite bad, right? It's predicting something really below. On maybe this point right there, it's really, really bad because it's predicting something way, way up, high above. Okay, so there's something kind of going wrong with our model here. And this is going to bring us, of course, to the idea of overfitting, generalization error, and cross-validation. So the fundamental problem here is that even though we set out to minimize this problem, right? This is sort of the problem that I've described as the problem that every machine learning algorithm solves. But even though we're trying to solve that problem, it's not actually that thing that we care about, right? We don't care about minimizing our loss on our data points that we see. We already know the answer for all of those data points. It doesn't really matter, right? Those things don't matter. You can just memorize a data set and get perfect accuracy on those points, but that does not really, that's just like a lookup table. It's not really an impressive algorithm here. What we really care about, and again, this can be made much more formal, but we're not going to do that here, is that we care about how well our function will generalize to new examples that are in some sense drawn from the same distribution of examples that we're training on. Right? So what we care about is not how well we can look up past peak temperature or past peak demand. What we care about is, for tomorrow, a day that we haven't seen before, if I use my model to try to predict what the peak demand will be, how accurate will that be? Right? So there's this obvious kind of mismatch between what we're minimizing in a machine learning algorithm and what we actually care about doing well on, which is the generalization performance. And this phenomenon of fitting your data very well, but fitting the actual underlying function that we sort of believe in our heads to exist poorly, this is a phenomena which you probably have, at this point, heard this term enough, but it's the phenomenon called overfitting. So you have low loss on your training data, but actually high loss, actually high generalization loss or generalization error when you try to predict on some new point. And the cartoon picture here is something like this. So there's some notion we have of model complexity, right? So this is like higher degree polynomials are more complex, maybe more nonlinear features are more complex. We'll see other classification algorithms like neural networks later on in the course that are also more complex. And the idea here is that when you increase complexity, as you increase complexity, your training performance, your training loss will always keep decreasing, right? This is the thing you're actually minimizing. Of course, it's going to keep going down. That's assuming you can actually solve this efficiently and everything like that, and it could plateau certainly. In fact, once you get zero loss, it will never get any better. But it will keep strictly non-increasing. But at some point, you'll reach kind of an inflection point here where your generalization performance at first also improves, right? If I have a zero complex model that's just like predicting a constant term the whole time, it's probably going to be pretty bad. As I increase complexity, it does get better and better, but at some point here, it kind of ceases to improve and then it starts getting worse. And this, while this is a cartoon here, this is a pretty good representation of the actual performance, or actually what really happens in practice. And we'll show some real plots in a second on these phenomena. Let me go back to this. So let's see what this. So the question is sort of what do we do about this, right? We don't have the mechanisms and what I've talked about so far to really address this problem here, because you just want to minimize loss, and minimizing loss, more is always better. So the strategy here is one that's called holdout cross-validation that we're going to employ to address this issue. And it's probably something you've seen before, I'm sure, if you've done any kind of data analysis. But what we do is we take our whole data set. This is our past training set. So the data that we have that has both the inputs and the output and the label. And we split it by some proportion here, where, say, we treat half of it as our new training set, so what we're calling a new training set, or sorry, 70%, I have in the slide. 70% is our new training set. And the remaining 30% is what we call a holdout or a validation set. Now, importantly, I'm not using the word test set there. It's actually a very, very important distinction. I'm going to come back to test sets next lecture when we talk about evaluating machine learning. But it's important, this is not a test set. A test set is what you actually report performance on. This is what we're going to be using. A validation set is what you use to optimize the hyperparameters of your algorithm. So sort of the meta parameters, like what's the degree of the polynomial, and a few other things that we'll talk about later. But for now, just know that I'm only going to be talking about validation sets, and that's an intentional terminology there. I'm not talking about test sets. And again, I'll distinguish between those much more next lecture. So the idea here is that we're going to train the algorithm on this new training set, but we're not going to ever show it. When we solve our normal equations, we're not going to show it any of this data. But then we're going to evaluate how well it performs on this data. Okay? So train it on this and evaluate it on that in some sense. Why 30% and 70%? That's just completely kind of ad hoc to a large degree. The idea is you want some substantial size for your validation set. If you have one example, it isn't going to be you're not going to have a very good estimate of your true loss, of your generalization loss. But if you make it too big, then you're not using all your data kind of efficiently to build your model, and so that seems like a bad idea as well. And so, for lack, 70 and 30 kind of feel like good numbers, I guess is the best reason that I can really give. It depends on a lot of things. If you have tons of data, you might have a much smaller training set and a much bigger test set, or you might just throw some away. Whereas if data is really sort of scarce, you might use some other techniques like holdout, like k-fold cross-validation, which we'll talk about a little bit later. Okay, so here is some code that sort of does cross-validation. And importantly here, I am doing this I'm doing this in a randomized fashion. So this is not always what you want to do. But what I'm going to do is I'm going to take all my data, all my days of data, and I'm just going to shuffle them. And I'm going to take a random 70%. So what I do is I call a permutation. Oh, I also, by the way, call np.random.seed0. It's a good idea to always fix your random seeds. that just fixes the random seed generator for NumPy. It's very good to do that because otherwise you will not be able to recreate your old experiments. So it's going to be, especially when you deal with things like complex models like neural networks and stuff, just always initialize your seeds deterministically so you have an exact way of replicating results. You don't want to be in a situation where something depended on the initial. I mean, try a few out because your algorithm should not depend on the initial random seed. That's a bad place to be. But it's even worse to be in a case where you got it to work once and then can't ever find a way to make it work again, or you're finding something really weird where it had great performance and or really bad performance and you can never find that again. So, a general word of advice: whenever you call anything np.random.anything, always call np.random.seed beforehand. Could be 0, could be anything else, but just make it deterministic. Then I call permutation. So this generates a random permutation of all the integers from 0 to the length of our data frame. I create an index of training points that go up to the 70% of that permutation, and an index of the cross-validation points that go 70% on. By the way, there are sort of routines for this in like scikit-learn, but this is, again, kind of a simple enough thing that I just want to put the code that does it here. And now I scale the features, and one important thing is that I do scale the features here based upon just my training set. In general, all transformations you apply, like pre-processing steps, should be based upon just your training data, not the holdout, not the validation data too. That's actually not quite a hard and fast rule, because in theory, if you only look at the inputs in the validation set, it's kind of like maybe you could have used those, but in general, be safe and compute things like your normalization just based upon the new training data, not the validation data. Here I'm creating my x's, my x training, my x cross validation, my y training, my y cross validation, and I'm scaling them both by the training ranges. And now finally I'm creating my polynomials here. I'm solving my least squares problem. I'm looking at the error for cross validation, or the error for training set, and the error for the cross validation set. So a little bit involved there, but not too bad. And here I'm actually multiplying by 0.5 for convention's sake, but I didn't do that earlier, so maybe we should have just dropped that actually. Okay. So a lot of code there, but it's also hopefully kind of understandable what each line there is doing. Any questions on that? Again, this will all be in the notes, so once I get to them. So you'll be able to go through it yourself. Okay, now a little bit of terminology here. We refer to the theta variables as parameters, right? I've always been calling those parameters. Those are sort of the things that you the things that you tweak to minimize the sum of losses, right? The things that you choose to minimize that problem. We're also going to refer to the other quantities of the algorithm, like the number of features you have, the degree of the polynomial, the amount of regularization, which we'll talk about in a second, what that means and what that is, how that's related to this context here. But all these things that aren't parameters are called collectively hyperparameters. And the idea of cross-validation, and sort of in a sentence, is that you're going to use the training set to determine the parameters. That's the training process. But then we're going to use the validation set to determine the best value of the hyperparameters. So we're going to use our validation set to determine, what degree polynomial should we use? What should our regularization parameter be? These kind of things are all going to be determined from the validation set because they can't be determined from the training set. The training set, you would always say more features is better. Just keep increasing. But the cross-validation set will actually give us an S, because we're sort of looking at data that hasn't been seen, hasn't been explicitly fit to, we can actually get an estimate of what our validation parameters or what our hyperparameters should be. Okay, so let's look at this again. Here is now our new data set where we're showing our training set now in blue. I've just randomly sampled 70% and 30%. And our training points, our new training points are in blue, and our validation points or holdout points, those two things you can use, okay, it's not test points. Validation points or holdout points are in green here. So what I'm going to show is I'm going to show the error, both the training error and the validation error, that we get when we vary the degree of the polynomial in our approximation. And so here's what that looks like. So at first, we actually do benefit. So this is the real version of this figure here. It actually looks reasonably similar, but you have to appreciate the scales involved here. So this is our version of this figure that really is sort of on real data here. Here is our holdout error. Oops, misspelled holdout there, but holdout set in green and the training set in blue, and this is going to be the average square loss on the axis. And the average on the training set, things always decrease. It actually does go up here. That's just from numerical issues. In mathematically, it will always decrease. But just because when you have really high degree polynomials, you have really big or really small numbers, this could bump up a little bit. At that point, you shouldn't be at that point anyway, in all reality. So when that happens, things are going bad. But what's really striking here, of course, is that the training set goes down or mostly goes down. But what we see in the holdout set is after a certain point, of course, error just goes up really, really high. And it goes up incredibly high. This is a log scale. So we're talking about 10 to the 8th here. If I just predict 0 for everything, that's actually this point right here. That's a 0 degree polynomial. So that's just predicting a constant term. So this is really, really high. This is a really, really bad prediction, even though it's fitting the training set very well. And that is, in fact, the 50 degree polynomial was, in fact, this thing, right? And you can imagine that this is not a very good fit to our data, right? I think it's even worse in this case because we just happen to get a little bit unlucky here and have one of the validation sets outside the range of the training set. And so this point is going to have a massively high error for those kind of degrees of polynomial. All right, so this is sort of impressive, but maybe not that useful for actually deciding what our degree should be because they all kind of look the same after maybe 3 or so. So let's zoom in a little bit. So here's what it looks like in after we zoom in. So this is degree 0, just picking one. Basically, degree 0 is just picking a constant term. This is degree 1 that's fitting a line to it, which doesn't do well. This is a quadratic function. This is a cubic function. And after that, it maybe goes up, well, maybe you'd sort of say, okay, maybe up to I'd probably just pick cubic here. Maybe you could, convince me that maybe you get a little bit of benefit by going to a 6th degree polynomial. But after that, there's no real benefit from it. And after, soon thereafter, at least on this scale, you actually start getting a little bit of increase in error. And here you're clearly, no longer want to be making those predictions. So this, again, is what sort of the reality looks like for our increase in model complexity and looking at holdout set versus the training set. See where the poll was. I think hopefully we'll get to the poll today. That would be a shame if not. Okay, so any questions on that? This is probably things you've likely seen before if you've done any data analysis, but it's worth having these terms sort of very concrete because this is really the core of actually doing machine learning. If you don't do this kind of stuff, if you just fit your training data, you're going to be hopeless. Or if you even just think about a holdout set as being the only thing you evaluate on and don't have a separate test set, that's also going to be equally bad. Yeah.
Would you say that the holdout set is lower than the training set, which is not likely?
Yeah, so here, that's a good question. The question here is the holdout set error is lower than training set error. That's not likely, but it's just possible by random chance, right? These are both estimates in some sense of the true underlying error. And so if you happen to get an easier set of points on the holdout set, you might have slightly lower error, but it's not a regular occurrence. Yeah. Yeah. The question is, can a linear model overfit the data? Yes, absolutely. So if you have enough features in your linear model, so they're different raw inputs like the temperature, the humidity, the whatever else, right? Those are then sometimes it's a pure linear model in that you're not computing any polynomial features. But if you add enough of them, you'll still have the exact same effect here. So really, things like feature selection are really crucial here, and I actually may switch around the feature lecture to talk a little bit about feature selection because it is a really important point. but yes, there's nothing inherent about linear and having nonlinear functions of your data. It really is about the number of features you have in your algorithm or as input to the system. Okay, the question is, how do I explain the peak here? And why it goes up there and goes back down? Okay, that's a good question too. So when you have things like polynomials, they are going to fit the data in odd ways depending on just sort of happenstance, right? So if you have an odd function, I'm trying to fit a certain set of points, and then an even function try to fit the same set of points, it will make sort of odd choices about the direction to go through. So maybe if I have an odd function here, so maybe if I have this function here, with a certain degree polynomial, it'll pick kind of to go down this way. With the other one, it'll pick to go up this way, right? There's all these sort of like random changes that happen when you change your degree of polynomial here, because ultimately, it's trying to find the best fit of all these features added together. And so, sometimes you might kind of have a curve that goes up here and down here. And so that can create random fluctuations on your validation set. But clearly, the thing you should be looking at is not those random fluctuations. You should not say, and this is actually where we're going to get to the test set later on. These things here, in general, this is all just random. This is all just sort of noise here. What's actually happening is that you're just doing a horrible job of fitting it, and the fact that you're slightly better here versus here has no actual significance. And in fact, that wouldn't generalize to a different split of the data. If you just randomized differently, had a different holdout, different permutation or different random seed, you wouldn't have that same thing. So those are random effects of the fact that you have a finite data size, and they are not reflective of the underlying actual error. Yeah.
So based on the graph, what is the optimal?
Yeah, so that's a good question. So we'll go to the next one because you can't really see here. I would say maybe 3, right? 3 is a good point. 3 is right here. You always again, the ultimate, if I were just to pick the minimum of this, maybe I would say 6 is the absolute minimum, right? Maybe. But you also want to be careful about kind of basing too much of your decisions just on this holdout set too, because this is also just one random split of the data. And you can also make bad decisions based upon this. You can essentially, and we'll get to this again, I keep repeating this point, but we'll get to this next time when we talk about test sets. The fact that this holdout set is not a real estimate of your generalization error either, it's just a better estimate. So you don't want to base too much information on sort of minor effects on the holdout set. What you really want to do is you want to find something that you sort of believe yourself for your own reasons is kind of the right type of model and go with that. And here I would sort of argue that we see big improvements up until degree 3 and then less improvement. And if you looked at the data itself, you sort of see that a quadratic function wasn't quite right, but by a cubic function it looks pretty good. And I would just sort of leave it at that probably if it were me. All right, so there are a few variations on cross-validation that you should know about, just at least by name. A common one is k-fold cross-validation. Frankly, actually, people often call k-fold cross-validation just cross-validation, but it's not. Cross-validation is when you hold out any amount of data and test on it. K-fold cross-validation is when you divide the whole data into k different folds, they're called, so k different subsections. It can be sequential like this, or it can be just randomized. They're usually randomized in the same way that cross-validation is randomized. But you separate into k folds, and then I run actually the algorithm k different times. Each time training on k minus 1 of these, and then testing on the remaining k. Then I train on the fold 1, leaving out fold k minus 1, say, training on folds 1, 2, k minus 2, and fold k, and test on this held out one. Then I hold out this one and test on these remaining k minus 1s. So in each case, you are training on all your data except for a small portion, and then evaluating that small portion. You're also, there's some advantages here. So in k-fold cross-validation, every example in your training set enters the validation set at least once, right? So you're, in some sense, maybe less sensitive to the whims of your random seed, right? If you have one really nasty example, maybe, you shouldn't try new random seeds until you get that one out of your test set, right? That isn't a very good way of doing things, and maybe you feel that it just isn't. It's a real point. You should really consider it. It's not a real outlier. You need to factor that in. With k-fold cross-validation, it'll always be in the validation set once, so always factor it in. And typically, it's common to things like report the average error over all the folds. There is, however, a very big caveat here, is that this is not magic either, because the actual training, the actual algorithm you train in the different folds, they're not independent. So it's not like you're doing k-independent runs here. They're actually highly correlated because they have most of the same data, just a little bit of data different. And in fact, this actually gets to an extreme when you have a method called leave one out cross-validation. So this is the extreme version of k-fold cross-validation, where you leave each example out, train on the remaining examples, and then evaluate that one example. So that seems like it should be really good as an estimate. And actually, there's something kind of amazing that happens, is that with least squares, there actually is, through some tricks of linear algebra, there actually is a way to compute the leave one out cross-validation error exactly with the same complexity as just solving least squares once. So I won't go into that actually, but you don't need to solve least squares k different times. You can just solve it once and get the actual holdout error just by a little bit some tricks of linear algebra. But the flip side is that this actually is not done that often, because again, all those different estimators you have that you formed are highly correlated. So it's not like you have a nice independent sample of k different, or in this case m different classifiers and m different error estimates. In the end, there's actually, for example, very little proof that this gives you any better estimate than just holdout cross-validation with one random seed done once. And so unless your data is really precious and you really need to include absolutely all of it in the test set and training set once, just to stick with normal cross-validation. Don't do k-fold cross-validation. Just stick with normal cross-validation. Also, a warning here. It's not even the right thing to do sometimes. So for example, for time series data, if I'm doing a time series prediction task, you should always have your validation set be the final elements in your, I'm actually not doing that here, right? But you sort of think that, maybe temporally peak power demand isn't that, it's somewhat independent each day. But if you have some sort of time series task that's sort of very kind of dependent day by day, and you run k-fold cross-validation, for all of your folds, or for most of your folds, you actually be using some future data to predict the past. And you can't do that, of course. You can't use the future to predict the past. So that might give you a very bad estimate of how well you're really going to do on future data. So in time series data, it's almost always better to have a single holdout set that involves future data. And in fact, for most cases, even for things like power prediction, I would actually do that. I would actually have my holdout set be just years n minus 1 and n, and then my training set is years 1 to n minus 2 or something like that. Yeah.
K-fold cross-validation, the different runs in the setup are independent.
Correct. Yeah, so the question was, can you explain more what I mean about there not being independent? So this is again a little bit, I don't want to get too much, because statistically, it means something very specific from a stats perspective, but I don't want to get into the formalities here. The way you can think about it is, if I was able to sort of sample data at random, and then sample my training set at random, and then also my validation set at random, that would give me kind of a single nice sample of things. If I could repeat that process and sample a brand new random data set from my distribution, and then a brand new generalization set, in that case, I could actually do things like average those two generalization errors and have that be a much better estimate of the true generalization error than each one independently, right? The problem here is that this is not what's happening. The data, of course, across the different K runs is actually almost entirely overlapping. Only one set differs. So the actual classifier or regression or parameters you're going to get out of those things are correlated across different sort of K-fold runs. And this makes it such that the average error here is not that much better an estimate of the true generalization error than just normal cross-validation. You don't get the normal effects of averaging produces a better estimate than just a single point prediction. Yeah.
So in previous cross validation, you said that the validation data should be at least 30%. But here the validation data would be very low.
Yeah. So the question was, I said here it's to be 30%, and oops, where did I put it? Here it said 30%, and here it's very low. But the point is, here you're actually you're using actually all the data at some point in the validation set. So it's low each time, but because you're using all of it, you actually, in the end, seem to have more total points to look at in your validation set. So that's why it can be appealing, but again, with a caveat that it's not actually as good as you think it might be.
But again, like, since we are fitting the model 3 times, so all those models could be doing bad because the validation data is less as compared to the older cross-validation.
I'm not quite sure I follow. So if you train it, why would the model do bad? You're training the model on more data each time.
But again, the validation data is, how can we be sure that it is doing better?
Well, so the question is sort of, I think it's sort of, because each validation set is small, it could do bad, but it also could do really well. So the idea is these would average out. And some data points you do really well on, some you do badly on, but in average, you're actually getting somewhat of a better estimate. But again, I don't want to push it too much because it can be good, but it's not as good as you might think it would be. The one last thing I'll say is that, and I probably do want to move on to the next topic to finish that this time, is there's also a technique called stratified cross-validation where you want to keep an approximately equal number of, say, positive and negative points in your training set as in your validation set. This is very important if you have very unbalanced data sets. So if I have only a few examples of a certain class, then I want to oftentimes want to make sure that I have that same percentage across my different folds. Otherwise, I get this phenomenon like if I pick a random seed badly, I get no positive examples in my validation set, and that's not a very good indicator of how well I'm really going to perform. Okay, so I actually do want to move on, and I want to finish this section before we finish today. Hopefully it won't be a problem, but I do want to get through it. I want to talk about regularization now. So far, we've sort of defined the complexity of the model in terms of the degree of the polynomial that I use within that model, right? That was our kind of very intuitive notion of complexity of a model. But it turns out there's actually another way we can control the complexity of models with a technique called regularization. So one kind of interesting thing happens here. So if I look at my 50-degree polynomial fit to my data, the way it's able to do this, so the only 50-degree polynomial is really kind of crazy in a lot of ways, right? These are really, really sort of highly variable things. They get really big quickly, really small quickly. The only way I'm able to pass exactly through those data points, it turns out, is by picking very large coefficients for my theta parameters. Essentially very large coefficients on those polynomial terms. Now I'm picking them essentially so that they cancel out in exactly the right way, such that really big things cancel to exactly go through that data point. And so if you look at the actual values you get from your least squares fit for things like 50-degree polynomials, you get really huge values. This one is negative 3.8 million, positive 7.6 million, positive 3.9 million, et cetera, right? Negative 26 million. They're really large values, and that's how the polynomial is able to sort of maintain that degree of complexity while passing exactly through your data points to minimize the error. Right? So we're having really big, the way we attained those really low errors on the training set was having really big magnitude weights. And so this suggests another way of keeping model complexity down, which is to keep the weights small. We actually already talked about this last time just because support vector machines always do this, so I just mentioned this term before. But now we're going to define it a little bit more formally. So this is a notion of regularization. Actually, I don't want to have that 1/2 there. Hang on a second. It's a force of habit for me to put like these 1/2 terms, but I'm gonna get rid of it. Okay, that's better. Okay. Much better. Okay, so what we're going to do is we're going to add to our objective function. So rather, again, remember, our objective before was minimizing the sum of losses squared. I even have it over here on my document cam. Unfortunately, I've blocked it off already, but I guess I'll just cross out this little edge here. We're going to add another term to this optimization problem, which is to say we also want to balance between minimizing our loss and keeping our weights relatively small. So we're going to add a term which is equal to the sum, some constant lambda, some positive constant lambda times the sum of all the squared values of our weights. So if the weights are really big, this term is going to be really, really big. If they're small, it'll be relatively small. And this lambda parameter controls how much emphasis we put on keeping the weights small versus minimizing our loss. So obviously, if lambda is equal to 0, we just ignore it entirely, and we just make our loss small. If lambda is infinite, or as it goes to infinity, it's never worth it to put any weight on our parameters. So we're always going to choose 0 for our parameters, and so we just choose 0. All right, so when we suffer whatever loss you get when you put 0 into your parameters for your hypothesis function. And this is going to be, and I should actually sort of, clarify that really this is the canonical machine learning problem. So it actually is this whole thing. It's the sort of the canonical problem, not just the first bit. Because virtually on every sort of machine learning problem you see, you will almost always have some regularization term to keep down the complexity of the model. And that will be a very common thing you see in sort of real machine learning algorithms. And again, by varying lambda from 0 to infinity, you can kind of sweep out the whole space of model complexity. One other thing that's nice about this is that in some cases, this is very easy to incorporate into our machine learning algorithm. So I'm going to give one example of that, and you'll kind of have to trust me on this a little bit. We're going to think about the least squares loss. So remember, our least squares loss was to minimize over theta the sum from I equals 1 to m of theta transpose xi minus yi squared. And then we're going to add this lambda regularization parameter here. The sum from j equals 1 to n of theta j squared. Oh, by the way, I should also say this whole thing can also be written as just the L2 norm squared of theta. And so I write them both ways in the notes. The sum of the L2 norm squared is the sum of the entries squared. So that's the same as the sum that I'm writing there. Okay, so this is the kind of thing you might want to sort of go through yourself. I don't want to derive it in its full form, but the gradient of this thing, the gradient of this guy, I'll call this whole thing our new sort of objective there. The gradient of this is equal, and I'm just going to go straight to matrix form now. We already know this one, so we already derived this one. This one is equal to x transpose x theta minus y. So I'm not going to go through that one again. It took a while last time, but we're going to just trust that we knew it. And the gradient of this thing is actually very easy, right? So the gradient, the partial derivative of this thing with respect to a theta k term is just going to be 2 theta k. I should also say there's actually a 2 here. It's going to be 2 theta k. So the gradient of this thing here is just equal to 2 lambda times theta. Because the partial derivative of that thing with respect to theta k is just theta k, 2 theta k. And so the gradient here is actually a very simple one. It just is the parameters. If that, by the way, was a little bit too too fast. I will have a little bit more description on the notes on that. I actually have those in the ones that are up right now, because I do cover that a little bit in classification with support vector machines, but hopefully that was understandable. Okay, so now sort of we just kind of do the same thing we did with least squares. So we just rearrange terms here. So this, we're going to try to set this thing equal to 0. Make it equal to 0 to find an exact solution. So I'm just going to expand this out. We have 2x transpose x theta minus 2x transpose y plus 2 lambda theta equals 0. So let's group together terms that depend on theta here. So we'll have 2 x transpose x plus, what it really is this lambda times the identity. It's important to sort of throw that in there because like this is really, you know, the identity times lambda, because of course that's fine, but when you lump it in with a matrix, you have to make it the identity. Times theta is equal to 2x transpose y. And so theta star is equal to x transpose x plus lambda inverse, so plus lambda I inverse x transpose y. Okay, and so the only difference actually between this and the least squares solution is just this additional term here. You're actually already using that in your homework. So we kind of justified it as saying this makes the matrix invertible, ensures that it's invertible, and it does do that. But actually it can be seen as a type of regularization. We're adding a little bit of penalty on making the parameters too big, and that prevents you from sort of having really badly conditioned solutions. Okay, so what does this look like? Here is our 50-degree polynomial. So not too good, right? It looks like a pretty bad fit to the data. Here's what happens if I fit the same thing, but I regularize my coefficients with lambda equal to 1. So all of a sudden that looks sort of amazingly good, right? And that's kind of amazing, right? I mean, it's a 50-degree polynomial. We could be horribly overfitting this data, but just by penalizing high weights in our polynomial terms, we're actually able to get a very nice fit to the data. Again, kind of ignoring what happens outside the bounds here, because what happens outside the range for polynomials is weird. Other functions deal with it a little bit better than polynomials do. So here is now the plot of cross-validation loss as a function of regularization. So the important thing here is that this is the same figure as before, but it's just in reverse. Because with regularization, a high value regularization means low model complexity. It means we're getting to the 0 model. Whereas a low value regularization means high model complexity. It means that we're just sort of not regularizing at all. So as we start off here, this is actually just the 0 solution. And so our training and our validation error are really close, but they're both really high. So that's not very good. As we decrease it, we kind of have this nice sort of sweet spot here, which is actually pretty big, which is a nice thing of this, where we still have training and validation error close to each other, but they're both fairly low. And then of course this is for the 50-degree polynomial, I should add. So this is for complex model class. This is what it looks like. And then when you start getting below a certain point, now you really start getting into the regime of overfitting, where your training set performance is great, but your holdout set performance is quite bad. So this is sort of another view of how you fit or control the complexity of your model. We can again sort of zoom into this kind of sweet spot region here. And there's a little bit of variation here, but this is all pretty good. This is all pretty low error, this whole band here. And so, we're picking, I guess I picked this point right here. Seems like a good point to pick. That's lambda equals to 1. But there is a pretty wide range of good lambdas. Also importantly, I am plotting here lambda on a log scale. Lambda really varies on a logarithmic scale here we're talking about. So if you're doing bad, if you want to sweep regularization parameters, don't go like 1.1 and 1.1 and 1.2 to 2. That's not you need a big range of these things. And you need a logarithmic range for these things. Okay, so now let's just do a poll to see who was paying attention through all this. I think it's a pretty factual poll, this one. Oh, and actually don't answer just yet because I realized I didn't. I want to make sure I selected the multiple choice answers here. But okay, so we run linear regression here, and with polynomial features, for some, it doesn't matter what it is, just some initial guess of d and lambda. And when you find that your validation loss is much higher than training loss, if that's the case, which actions here might actually help? Can select more than one, but decrease lambda, decrease d, and increase d. Let me go and open up the poll, but I also have to edit the poll before I open it up, so give me 1 second. You can think about it in the meantime. Okay, so approximately, I should just close that, hang on. Approximately 3/4 of the class or so was listening, maybe. Okay, so who wants to say which answers are right here, or argue for certain answers being right? I guess. Who wants to argue why you should? I guess who wants to argue the first one? Who wants to argue why you should decrease lambda? Yeah.
It could be too large, so you have the model where all the parameters are 0.
So okay, so it could be too large. So you have all the parameters are 0. So let's see how I phrase the question. So I phrased the question that your validation loss is much higher than your training loss. I guess I didn't say your, I said you training loss, but the idea here. Oops, let me go back. I hate this how this does this. Okay. So it says that your validation loss is much higher than your training loss. So in that case, there really is no way that we're in this regime over here. Because in this regime, they're both bad, but they are the same, bad. So what are some alternatives you can do? Decrease it, yeah. Or sorry, who says increase? Yeah, sorry, what was that? Increase lambda, yeah, that's a good choice if you can't decrease it. Right, so essentially what's happening is that we're in this regime here, right? We know we're in the regime where our training loss is much higher than our testing loss, i.e. we're overfitting to the data. Sorry, our validation loss is much higher than our training loss. I said testing loss there. I really tried to avoid it this entire time. Slipped up into it. We're over here, and so we know that it's not the only thing we can do. We can also change our features, but one thing we definitely can do is we can try to increase regularization to the point where they at least reach the same level. So we want to increase lambda, because again, increasing lambda decreases model complexity. What else what else should we do, perhaps? Also want to decrease d, right? That's for the same reason. D is this version over here. We are in this regime over here. So we can decrease d to try to get into this regime. I should add, when you do data science in practice, it will not always be this nice. This happens when you have a model somewhere in your class that will actually fit the data well. What often happens in practice is that you are overfitting. You have too complex a model, so you overfit. You increase regularization, and then they both do badly. Right, so at first the training loss looks great and test loss looks really bad, or holdout loss looks really bad. I should have like a tip jar I put money in every time I say test set. You could be you're in the regime where you're over here, and you start decreasing your complexity, and you nicely just slide right to the point where your 0 model is as good as anything. So be aware that this is not always the nice picture that you really see in practice, but this is the cartoon you should at least have in your mind. And if that's what happens, then really there's nothing. What that's telling you, if you have the other case, well, actually, it's actually a good example. So, for example, if my data is random, right? So if I have random features and random output, I actually can fit it quite well on the training set, right? I can get good test error. I can get good lower performance here. My generalization performance will always be bad, and eventually will get even probably worse. But if I start decreasing my complexity, I'll just approach the point over here where I'm basically just predicting nothing all the time, because that's all the signal there is in the data. You can't predict anything random. So be aware this is not always what happens, and we'll actually cover this a lot more when we cover debugging data science. The alternative is not just that you need to tweak your model or anything, it's whether you need to really think about, is there a signal in my data that tells me what I want to try to predict? So don't think you can always just tweak one of these things, but you surely can't hurt by decreasing your regularization in that case, for the most part. I mean, modulo some odd effects, but you probably want to increase regularization, for example, if you're in the regime of overfitting, or you want to decrease model complexity. Okay, so I think I'm actually going to stop there. We're 5 minutes early, but I go over by a minute or so each time, so I owe you guys a few minutes. Rather than starting on general nonlinear features, I'm going to wait till next time, and we'll cover that next time.